Hi everyone. Hi everyone. This is Shri. I'm currently recently completed my master's from UCSD. Now I'm gonna explain a paper that is on adapting while learning, which is where we grounding up the LLM system with intelligent tool usage adaptation. First of all, this paper is really an interesting one written by my UCSD research team, and we now delve into the explaining of a paper. Coming to the initial introduction, large language models have shown promising capabilities in addressing scientific problems, yet their performance diminishes when faced with the complex challenges or like complex queries. But while integrating LLMs with the tools improves reliability, this often leads to an over-reliance on the tools, which reduces the model ability to solve simple problems independently. And idea is inspired by the how the human reacts to the solving the queries based on the human problem solving behavior. There, initially, now we in this paper, a novel fine-tuning framework comprises of world knowledge distillation and tool usage adaptation has been addressed. This approach allows LLMs to adaptively decide when to use the external tools and when not to use, which relies on the internalized knowledge. Our method aims to enhance the LLM problem-solving capabilities across diverse specific domains by combining domain expertise with the intelligent tool usage. As I was saying, this has been inspired by the human idea of solving a query. First component consists of an internalized domain world knowledge distillation. The second component is for the tool usage adaptation. So finally, this paper proposes a novel training paradigm which comprises of two components. The first component has world knowledge distillation, which uses supervised fine-tuning and preference learning optimization to align a pre-trained LLM with the highly accurate solutions generated using information from external tools, which aims to internalize scientific knowledge. In the second component, tool usage adaptation um, is evaluated on the LLM and it classifies the questions as easy or hard based on the model's accuracy, while maintaining the same alignment target for the easy questions. Then we, then they then the researchers has trained the model to follow external tool traces for hard questions, enabling intelligent switching between based on the problem complexity. That is often more introduction. And coming to the second page. So our contribution is summarized as follows. They have introduced a novel two-stage training paradigm that enables the LLMs to adaptively solve real-world scientific problems of varying complexity. Further, they consider tested it for the four different data sets domains, including both questions and the solution, to facilitate future research in this direction. Coming to the background work, previous researchers has explored these various strategies for enhancing the LLMs, like which includes supervised fine-tuning, RL, and tool integration. But like approaches like physics simulators, climate models, and competition have shown potential in grounding the LLM to the domain-specific knowledge. However, these methods often lack adaptability, resulting in tool over-dependence or limited knowledge transfer technique. But the techniques like preference learning and the prompt engineering have addressed some aspects of LLM alignment, but fail to optimize the decision making for the problem complexity. So by now we are integrating supervised fine tuning with the intelligent tool usage. Through this, our framework builds on this, creates more robust and efficient model. When you look at this picture clearly, what we come to know is like this demo, it is clearly demonstrating two methodologies for fine-tuning a long language models using tools and optimizing their responses for complex tasks. Delving into the clear explanation, coming to the first part, that is supervised fine-tuning. This section focuses on training LLMs to answer multiple choice questions with the external tools. Let's say the question example. The LLM is asked a question about the temperature change under specific scenario of CO2 emissions. Then it follows these three steps. First is retrieving the data. LLMs query external tools to retrieve the relevant data, such as the initial temperature and the scenario with the increased CO2 levels. And then emulating the scenario, tool simulates the conditions to provide the data points. and then computing the answer. The LLM uses the retrieved data to compute the change and select the correct answer. This is the first part, that is supervised fine tuning. And second thing is preference optimization. This section deals with improving LLM response for open-ended questions by ranking and selecting the best output. Coming to the question example, it designs a maritime route between the Busan and Margaret River to minimize the global temperature increase under specific constraints. The steps it follows is initially the LLM generates multiple outputs with the different approaches, and then uses external tools for evaluating these answers, and then getting often ranks for the each solution. Based on this rank, it will provide the output to the user. That's what is going on in this picture. The next page about the methodology. Like this framework involves two key components. As you all know, like first thing, world knowledge distillation, the tool usage adaptation. World knowledge distillation, it focuses on fine-tuning LLM solution generated with the tools and by enabling them to internalize domain-specific knowledge. Tool usage adaptation, it partitions the problems into easy and hard categories based on the model's direct answering accuracy. For easy problems, the models generate solutions without tools, while for the hard problems, it learns to leverage tools intelligently. This combining strategy approach, like it balances both internal knowledge with external tool usage, and ensures adaptability across various problem solving complexities. Coming to this world knowledge distillation methodology, when you look clearly at this equation, its purpose is to adapt the alignment laws defined in the equation specifically for the world knowledge distillations. Coming to the interpretation, the WKD, which is the world knowledge distillation, it fine-tunes the model to internalize the scientific knowledge by solving the problem independently without relying on the external tools. This is ideal for simple problems. This is like ideal case for simple problems where the tool usage is unnecessary. But in the complex scenarios, tool usages become highly important. Yeah, coming to this equation. In this equation, the loss function is defined for direct fine-tuning of the model to align its prediction with the given dataset. The key components D is the dataset. Pi theta, this is the model's probability of predicting Y given input X and prompt B. The information from the external tools using during the solution generation processes. Interpretation. Coming to the interpretation part of this equation, in this, the loss is penalized by the model for deviating from the correct solutions in the training dataset. It encourages the model to learn to generate correct answers directly when the external tool information in the prompt PF are provided. So this model has been tested on the two existing public datasets, Math and Skybench, and it constructs 4 new specific datasets for our experiment. Mijoko for partial differential equations, climate sciences, and epidemiology. And also they have used a Llama 3.1 8B instruct as a base model for training of a scheme. And they also conducted the extensive evaluations of other sort of open and closed source models, including GPT-4o, GPT-4o, Claude-3.5, and Llama 3.1 70B instruct. So when like they have a clearly observed a 28% increment in the accuracy through this framework compared to the baseline. And like this method substantially outperforms all the baselines on custom created datasets that were not commonly covered in the pre-training. So you can clearly see this, the functionality of subcomponents, their case, hard not choosing tool has more proportion compared to the remaining all other cases. Coming to the conclusion of the future work, this work introduces a novel framework for grounding the LLMs in scientific problem solving by integrating the domain knowledge and the adaptive tool usage. Our method significantly improves the model accuracy and the efficiency, making LLMs more reliable and versatile by emulating the human-like decision making. This approach addresses tools over reliance and enhances knowledge retention. Future use could be like improving the domain specific to the cross domain that I'm currently working on, and like our work and this work serves as an a foundation for developing intelligent AI scientific assistants, and this has been funded by US Army research team. So that's going well, and like, yeah, that's it. Thank you.